Hello everybody. Support optimization is a process that will allow users to set up the model and have the software locate the best places for the supports faster than a user can do this manually. Today's session, we will look at the support optimizer's genetic algorithm. We'll understand support optimization workflows. We'll look at the setup of the support optimizer in AutoPIPE. We'll review the results from the optimizer, and we'll look at some special considerations. Every piping system will have geometry constraints and a set of loading conditions to be satisfied against a requirement of a specific stress design code. In addition, we have load capacity of supports and equipment nozzle limits to consider, as well as minimum deflection of piping. As some of these conditions are conflicting, manually determine a satisfactory route and support configuration can be a time-consuming process. Experienced pipe stress engineers can iterate to a satisfactory solution quicker than an inexperienced one. But even so, it can still take many hours or even days to come up with a working solution for a complex and constrained system with a variety of loading conditions. The support optimization feature in AutoPIPE uses an intelligent genetic search algorithm that follows an evolutionary approach to compare thousands of design alternatives. The algorithm is a learning algorithm, a sort of artificial intelligence, learning from the failures and promoting survival of the fittest. For a given pipe stress analysis problem, the support optimizer feature automatically considers thousands of solution configurations and weeds out the invalid trials that do not satisfy the specified design criteria. This design criteria is taken from a stress model. In addition, support groups and locators are set by the user. From the results, the user can easily review and compare many different solutions in real time as they are produced, and ultimately select the best and most cost-effective design. A valid solution can then be used as a seed. The nature of the genetic algorithm is that it can take a different branch if provided with a direction or a seed. Ultimately, this can lead to a different solution. Okay, a little bit about the genetic algorithms process. Very simply, these kind of algorithms are known as evolutionary and work on the basis of natural selection and survival of the fittest. It is also stochastic in as non-deterministic, and similar runs can result in different results because of this. The first process is to initialize by randomly creating possible solutions. These solutions become the individuals in the population. We then evaluate these individuals and rate them using a fitness function, and penalize failing solutions and learn as we process. We then select individuals based on their fitness to become parents, to produce children, and these are the new solution individuals. Mutate or improve these children and then go round again. In this way, the population evolves over each iteration, with more fitter solutions dominating it. At each iteration, the population is added to and further evolved, rather than considering a single point in a deterministic sequence of points, as in a classic algorithm. And this is the main difference of genetic algorithms over classic algorithms. Jessica will now discuss the workflow and operation and setup of this new AutoPIPE feature. So over to her.
Thanks, Bill. So let's review the workflow of the support optimizer. There really are two workflows. The first one is what the user sets up and sees, and the second one is what the optimizer is going to do behind the scenes. So you can see it's very complicated, and this is just going to be a high-level overview, and then we'll discuss each part in more detail. The user first creates a pipe stress model either manually or through import, and then he defines the loading definition in the model. Support locator groups need to be defined, which requires the user to make sure the supports and the support assemblies are correct for their specific model and needs. Once the support locator groups are defined, the user must insert the support locators along the piping model and assign each one to a support locator group. So just going through those steps. Next, the configuration options are defined, and the design criteria for optimization has to be defined also. At this point, the model must be validated by running the consistency checker. If errors are reported, the model must be reviewed, and all of these steps have to be gone through again until the model is validated. Once the model is validated, the job can then be submitted. This is where the optimizer gets to work. The optimizer will run through all of the configuration options and design criteria that were set up by the user. For example, evaluating sustained, thermal, and occasional stresses, reference points, support loads, and rotating equipment limits. If the solutions do not converge, the optimizer is going to add, delete, or modify supports at the support locator locations until the solutions do converge. If the solution does converge, it will be reported to the user in AutoPIPE in a list of top solutions. From this list, the user can launch an AutoPIPE session showing each solution to evaluate those top solutions. If the solution looks good, the optimization is complete. If not, the user has to start again with updating the model. So let's dig deeper into these different parts. The support locator group dialog allows you to insert support locator groups into your model. The user can assign a group name along with 5 assembly options. The user can pick from assemblies of single supports or multiple supports at one point, or can select none if 5 aren't needed. The available support assemblies can be reviewed by clicking on the Support Assemblies button, and using this, new assemblies can also be added. The user also has the ability to force the optimizer to place the same support at all locators assigned to this group. And an example of this would be maybe for like a pipe rack type of situation where you just have guides along the entire piping. To insert support locators, the user first has to select the points in the model where locators are wanted. These are locations where possible supports will go. Then the user can insert the locators. A locator group will need to be selected while inserting the locators, so if selecting multiple points in the model, be sure to select points that the same locator group should be applied at. So this might take a few rounds if selecting and inserting locators of multiple groups are to be added into the model. For a selected locator group, the selected assemblies will be displayed, but they can't be modified here, so they'll be shown as grayed out. The user also has the option to fix the existing supports for optimization. This can be used for pre-existing supports that should not be changed by the optimizer. Once the support locators are added, the model will look something like this, with the locator graphics showing. The support optimization dialog is where most of the optimization options and design criteria for optimization can be set up by the user. The supports tab allows you to define a set of supports which can be used to create support assemblies. Each line in the grid corresponds to a unique support definition with a unique name. Support set information defined in this tab is stored in an XML configuration file. This tab is populated with the default AutoPIPE supports. Each support definition can have a unique associated cost. New supports can be added by typing into the last line And modification of the support properties or deletion of supports is possible, similar to the input grid in AutoPIPE. The Support Assemblies tab is where you can define a support assembly based on existing supports defined in the Supports tab. This tab is populated by default with 12 assemblies. The user can add assemblies by assigning an assembly name and selecting the appropriate supports defined in the Supports tab. As an example here, we could add a 13th assembly with a combination of a guide and a line stop. The user can also modify assemblies similarly, or selected assemblies can be deleted. And the positive and minus signs allow the user to expand all of the assembly nodes in the tree so that their supports are visible, or collapse all the assemblies so that only their title row is visible. So the minus sign tree will look like this. So let's look at a quick example of adding supports and a new support assembly. First, on the Support tab, we want to add a V-stop with a friction value. The default V-stop has no friction applied. So we can add a support by just typing in the last row. We give it a support name, select the type, and add the friction value. Now we're still not able to actually add this support to a support locator group to be considered for optimization until they're added into an assembly. So let's say we want to create an assembly that combines this V-stop with friction with a line stop. We can easily do that. We can give the assembly the name and select the correct supports to be included. But even if we only wanted to add in the V-stop with friction as an option by itself, we still need to create an assembly for that. So again, we can give this one a name and just select that V-stop with friction support that we added in. After doing so, we now have the option to add this to a support locator group, as it now will appear in the pull-down menu under Assembly option. The Optimization Options tab of the Support Optimization dialog is where you select the design criteria to be used for optimization and to assign a relative importance to each criterion. If the Include checkbox is disabled, the corresponding design criteria are not considered in the optimization analysis. So consequently, the reported top solution may not satisfy those unchecked criteria. So make sure you check on to include any important criteria. The optimizer searches for solutions within the ratio limit that apply to all the selected design criteria. For a trial to qualify as a valid solution, it must have all selected design criterion lower than this ratio limit. Separate limits can be defined for each design criteria, as you can see here. Up to 4 stress categories are displayed in the design criteria. Each stress criterion corresponds to inclusion of all default code combinations of that category defined in the model. The first 4 stress categories that are available in the model's Code Combinations tab of the Load Combination dialog box are available in the Design Criteria table. If rotating equipment or reference points are defined in the model, enabling either criterion enables the optimizer to take all the design checks reported in the rotating equipment output report and reference point allowable checks into account respectively. So let's look at an example. Here we see the rotating equipment and reference points are the only including design criterion to be under a ratio of 1. The optimizer gets results in 12 minutes, and we see the top trial is trial 112 with 5 supports. So we can open the model for this trial. We can analyze the model for static and modal, and then we'll review the combinations. Where we want to select only the non-code combinations that apply for these results. Then we can select to review the equipment and reference point output reports. And we'll scroll down in the output report to review the different non-code combination reports and to see all of the calculated ratios for the forces and moments on the equipment. So we see a pump is defined here, and we can review the forces and moments at the suction and discharge nozzles and also at the pump center for all the different non-code combinations. After reviewing them, we see the highest ratio is 1.952, but this is for a nozzle loading factor of 2, so we can divide this and see our max is 0.976, which is what is shown in the results for the support optimization trial for rotating equipment. Next, we can also look at the reference point report and review the force and moments results ratios. For this, we see the max is 0.92. And again, this is the ratio that's shown in the results for reference points. The support forces design criterion corresponds to a check of the allowable support forces. The check is applicable to all supports in the model, and the support reaction is checked against the allowables defined in the support allowable table. The gravity displacement design criteria checks the maximum vertical displacement at every point in the whole model under gravity loading against the specified allowable displacement. The lowest frequency design criteria checks the natural frequencies of the model against the allowed lowest frequency. The natural frequencies for each support configuration must be greater than or equal to this allowable. If the use hanger analysis option is checked on, the hanger selection will be run before static analysis for trials with undesigned springs. The population size input defines the population size for each generation of the optimization. This is a critical factor that impacts the time and the results of the optimization. If this value is too large, the optimization process can take a lot of time, but it may result in a better solution. The minimum is 5 and the maximum is 1,000. The non-improving generations input defines how many non-improving generations the optimizer runs after the last generation where the best scenario was found. The parameter will impact the time and results of the optimization. The minimum here is 2 and the maximum, again, 1,000. The seed solution checkbox enables using the existing support configuration to start the optimization. This is also an option directly on the Support Optimizer ribbon tab. The user can provide a support configuration that provides a ballpark figure of the final optimized model. The optimizer will then take that support configuration and start optimizing from there onwards. The seed solution will act as a scaffolding to the more optimized solution. Before submitting the model for optimization, the status of the consistency checks must be reviewed on the Submit Jobs tab. Selecting this option automatically runs all of the consistency checks and displays the results. The optimization consistency checks dialog is displayed if one or more of the checks have not passed. So you may see warnings or errors in here. If they've all passed with no warnings and no errors, this dialog will be shown. The AutoPIPE help has more information about the consistency check messages with a clear explanation for each. The Submit button will be grayed out and disabled until there are no longer any consistency check errors or warnings. Until there are no longer any consistency checks errors being reported. At that time, the optimization process can be initiated by clicking Submit on the Submit Job tab. This tab also enables you to monitor the progress. The user can see the time that has elapsed since the support optimization job was submitted, or the total time to complete the job if it's complete, along with the progress which shows the current cycle and trial number. The user can also see the progress graph and optimization table being populated as the optimization is in progress. At any time, the user can click on Stop to stop the active job. However, the job will only stop after completing the current cycle. Once the optimization is complete, the user is going to see one of two messages. Either that the optimizer was unable to find a solution. In this case, it would be useful to look at the log file and see what ratios are failing and by what margin. and increasing the population size might help, or the user will see a message that the optimization is complete and the results should be reviewed. So let's dig a little deeper to understand the results. These can be seen once the optimizer is finished on the Submit Job tab, but it can also be reviewed directly from the Ribbon tab. The optimizer iterates through multiple cycles as it progresses. Each cycle is made up of individual trials or configurations of supports that are evaluated by the program. At the end of every cycle, a best trial is defined. The optimizer may need several cycles before finding a best trial that is a viable solution satisfying all the specified design criteria. The number of trials in a cycle is equal to the population size, except the first cycle, which we refer to as an elite cycle. The number of trials in the elite cycle is 1/5 the size of the population, with a hard-coded minimum of 3. The graph provides feedback concerning the progress of the optimizer. The feedback is in the form of tracking 2 metrics, the number of supports and the cost. Each point on the number of supports graph and the cost graph corresponds to the best trial in that cycle. The cost is calculated as the addition of the basic cost and additional cost of all the support assemblies defined by the user that are in the trial. The grid lists up to 8 trials selected by the optimizer, satisfying all of the selected design criteria. There are some solutions which are identical to other solutions which will be detected and ignored. In order to enable you to manually rationalize and optioneer between these top solutions, this table provides access to the models corresponding to these trials. So let's look at a quick example showing this. In this completed optimization, we can review the top solutions in the options table. We can select one of the top solutions and open it. AutoPIPE opens and we can review the model, including the support configuration. At this point, we could analyze and review the results or make changes, or we can choose to optimize again with this solution set as the seed file. So we run the consistency check to make sure everything is consistent and set it as the seed file, which we can also see on the optimization options tab, and then we can submit the job. The log file can be opened in Excel from the Submit Job tab or the Ribbon tab. This file provides information for each trial, its cost, normalized values for different criteria selected on the Optimization Options tab, whether the trial was a valid solution or not. The values are presented in ratios and are normalized by the support allowable where applicable. The PSO or Pipe Support Optimizer file of the model can be opened from the Ribbon tab. When consistency checks are run for the model, a value is generated with extension PSO. This file has the ratios of different design criteria in the Options tab. It will always have 9 values. The first 4 from the stress categories showing in the Options tab. Remember, these can be different for different models. The last 5 will be the last 5 design criteria in the Options tab, which are always the same. The first 7 values will be ratios of the respective design criteria. The last 2 values for gravity, displacement, and natural frequency will be the actual vertical displacement value and actual frequency value. These values will later be used in optimization to check against the allowable. AutoPIPE generates a PSO file for every support optimization run, which is then used by the optimizer to review the results for the run and determine if a run is resulting in a solution or not. This file is helpful to the user to identify which design criteria is failing in your current model if you're trying to submit something as a seed solution. And if it does not pass all of the design criteria, the program is going to report a consistency error. Anything that does not pass all selected design criteria is not a solution, and anything to be submitted as a seed file must be a solution itself. So let's look at an example of using the seed file option. This shows the original model with support locators included. And here are the assemblies to be included in the support locator group, which is the same across all of the locators shown in the model. I set up the optimization options as shown, including sustained expansion and hoop stress, and reference point loads, and gravity displacement as my design criteria. Once submitted, the job took a bit over an hour to run, and I was presented results that included 2 trials with only 1 support difference. So I wanted to see if I took these result models and I used them as seed files, if that would optimize the results even further. First, I opened up the model for trial number 129, which looked like this. With the same original optimization options set, I submitted the job, and I saw results in about 11 minutes with the solution optimized further. Compared with the original run, we see an improvement. Then I opened up the model for trial number 106, which looked like this. Again, with the same original optimization option set, I submitted the job. For this one, I also saw results in about 11 minutes, again with the solution optimized further, and it looks similar to the solution for the other seed file with 21 supports. Again, if I compare that to the original run, this was much better. So just comparing them side by side, we have very similar results with just some slight differences in the ratios. And after opening the optimized models and comparing the support tab of the input grid, we see just some slight differences in the support configuration. For instance, there's a support at A40 in trial 106, but not in trial 129. Let's talk a bit more about including spring hangers in the support optimization. In this example, all locators are assigned to the same support locator group, which includes a spring. If you remember, one of the optimization options is to use hanger analysis. So let's explore this a bit. If we first run the optimization without this checked on, so it's unchecked, we get our results in about 7 minutes. If we explore trial 60 first, we see the model looks like this with a spring hanger included. But looking at the spring dialog, it's still unassigned with no calculated cold load or spring rate. If we run the analysis, including hanger selection, static, and modal, we see the model ends up looking like this. The spring hanger was removed because AutoPIPE in this analysis determined it wasn't needed. Now let's look at trial 72 this time. Again, there's a spring hanger included in the model. Again, with no spring information defined. This time, after running the analysis, the spring remained in the model and the spring dialog became populated. Now let's look at running the initial optimization again, but this time with the use hanger analysis checked on. We get similar results with the top 8 trials, but some slightly different ratio values. Opening trial 60, we see the model was automatically assigned a V-stop at point B14 this time instead of a hanger, as in the previous run. Opening trial 72, we see there is still a spring hanger at point B5. If we open the spring dialog without running the analysis, we see the spring hanger is already assigned a cold load and a spring rate from the optimization analysis this time. Last time, it was undefined. Running the analysis on the model, including the hanger selection, static, and modal, does not change anything, including the spring information. So the importance of this is that if the user wants to include undesigned spring hangers in the final model, it's important to check on the used spring hanger analysis option to find the most accurate solution with the correct supports. Again, this is important if you're including support assemblies that include undesigned springs. Instead, the user could also choose to design the springs on this support tab by inserting the cold load and the spring rate and include those in their support assemblies, and then the spring hanger analysis does not need to be included before the static analysis. So I wanted to take this example a little bit further using these two trial models as seed files. Remember, we discussed the PSO file, which is generated when a consistency check is run for the model. This is showing the PSO file for the original model in this example. And we can see how it changes. Here's the PSO file for the trial 60 that we looked at on the left, and for the trial 72 that we looked at on the right. These can both be used as seed files in this example because they're both passing the criteria we have assigned, the 4 code stress ratios and the gravity displacement. The negative values that you see here just mean that the optimizer was not able to receive a design constraint check ratio value from the AutoPIPE design check post-processor for these criteria, which is okay because these were not criteria that were defined as part of our criteria for this example. So the original results are shown on the left, for trial 60 on the top right, and for trial 72 on the bottom right. And we can see the results were optimized a bit further in this case, but nothing too drastic as we already were down to only 3 supports in this case. The cost went down a bit for each of the examples using the seed file. So the optimization process is even more beneficial for larger models with more support locators, which was shown in our previous seed file example compared to this one. The last topic I want to cover has to do with linear versus nonlinear analysis. Remember that in AutoPIPE, the user can run a nonlinear static analysis to take into consideration support gaps and friction or the yielding of soil for buried piping. The support optimizer will also run nonlinear analysis if the source model has been set up to run a nonlinear analysis. If the source model is set up to run linear analysis, the support optimizer will only run a linear analysis. Nonlinear analysis can sometimes be more difficult than linear models to find a solution, but it's important to understand what type of analysis the optimizer is running and how to set it up correctly. We do have a frequently asked questions document available for the support optimizer, which has some suggestions to help you set up your models along with many other common questions about this tool. So let's just go back and review and take a look at the support optimizer workflow again now that we know a bit more about each part. First, the user creates the model and defines the loading. The user defines the support locator groups and adds support locators to the model. Then the user defines the configuration options and design criteria and runs the consistency checker. If errors are reported, the model has to be reviewed by the user and all the steps have to be gone through again. But if the model is validated, the job can be submitted. Once the job is submitted, the optimizer gets to work and runs through all of the configuration options and design criteria that were set up by the user. If the solutions don't converge, the optimizer makes some changes to the support configuration until the solutions do converge. If the solutions do converge, it's going to be reported to the user in AutoPIPE in a list of top solutions. From this list, AutoPIPE can launch AutoPIPE. The user can launch AutoPIPE and evaluate the top solutions. And if the top solution is acceptable, the user is done. If not, the user can update the model and start again. Thank you for attending the Bentley Tech Talk about support optimization. Here are some helpful links to my information along with Phil's information and our Bentley Pipe Stress Analysis YouTube channel and LinkedIn for Bentley Systems.
So Jason's asked 11 minutes runtime typical for 20 support system. Jessica, have you got any further examples on runtime? I can think of a few that I can mention if you can't.
Well, it depends on the population size. So I think in that example, I had a low population size of 10. If you increase it to 20 or 50, you'll see that increase drastically. So it really just depends on how it's set up, the optimization options.
That's right. And the bigger model that Jessica used as a seed example, the first one, that had 51 support locations and ended up with about 21 supports.
That took about an hour, again, population size of very low, of 10.
Yeah. So it's all dependent on the size of the model, the population settings, etc., as to the runtime. But pretty quick. 11 minutes is quite quick. Even 40, 50 minutes for that bigger model was pretty rapid. Okay, there's a couple of questions on functionality then, Jessica. So, do you have to use the default support assemblies?
No, the user can, I did show an example of that. The user can make changes to the default assemblies by either adding a new one, like I did in the example, or you can actually modify the existing assemblies or just delete those existing assemblies also if you don't want to use those.
Another one there. Do you have to assign support locators to points one by one, or is there another way of doing that?
As long as you have multiple points that you want to apply the same support locator group to, they can be assigned at the same time. So you can use your control or your shift or your select options and select multiple points and assign the same locator group. In larger models, you probably will have a couple of locator groups, so you just have to make sure you're careful in selecting the right points to assign the right locator groups.
Okay. Can you stop the optimizer anytime?
You can stop the optimizer. There's the stop button that I mentioned. You can click stop at any time. The optimizer is just going to finish the end of that cycle, so it's going to go through those. Let's say you have a population size of 10. It will go through those 10 trials, and then it will stop.
And do we have an input grid with any of these settings in it?
Yeah, we've added tabs to our input grid for both support locators and support locator groups, and so things can be changed right from within the input grid tabs, just like all the other tabs that we have available.
Okay, another question here on the cost. Costs look like relative to number of supports. It essentially is a factor of the number of supports. If you take the time to actually define the relative cost of each support type in your setup, then you'll get a more indicative comparison of cost. In some of the examples there that Jessica was showing, then the support cost were all the same value. So there was no difference in terms of types of supports that we use in terms of cost calculation. So you need to actually set up that relative cost difference of the support types that you've got in your model.
Right. So for each support, you have a base cost, a basic cost that can be assigned, and then as you create assemblies from them, you can add an additional cost, and that's what they're based on. As Phil said in my examples, I just had the default, which is a value across all of the different types of supports, but they can be changed by the user.
Another question. So the user decides what you are trying to optimize, correct? You can optimize on cost, minimum stress, location, number of supports.
Correct. You pick and choose which you want to what criteria you want to optimize for. You check that on, and you can sometimes you have to assign an allowable, for support forces or a different ratio. but you can pick that. For code stress, for the stresses, the most important thing is to remember is that it's just going to show the top 4 that are in your combination dialog box. So you may have to rearrange how those are showing in the combination dialog box to make sure you're showing the right stresses for your optimization options.
Can I continue using other applications while the optimizer is running?
You sure can. That's exactly how I was able to prepare for the Tech Talk and continue to work. You can actually have multiple optimizations running at the same time if you need to also.
Yeah, so it's running in background, so we can carry on working on whatever else it is you're doing. And does it optimize only on the selected load combinations?
Yeah. Yes. Right. So only whatever in the optimization options tab, whatever combinations are checked on for the criteria for that optimization run.
Yeah. If a particular load case didn't exist in the model, then the option wouldn't be there by default in the optimization selection. So you had no occasional loads, for example, there wouldn't be any need to check the occasional stresses, so it wouldn't be selected.
Correct. It would only show if there's only sustain, hoop, and expansion, then it would only show those as options in the criteria.
Yeah. Okay. That's all the questions that have come through.